what I like to think of as kind of the center of mass of evidence, right? And I'm starting to get some window into what your process is around selection of studies, and no one study being holy. But when you look at, as you mentioned, all the studies on fiber having a positive effect to some degree or another, it's pretty hard to refute that there isn't something really interesting there.
Yeah, and one thing I'll tell people is like, one study, I mean, sometimes I'll change my opinion based on a single study when it's really well done and very powerful. But usually like one study is just going to move me just a little bit, right? And then maybe if another one comes out, move me a little bit more, right? And then like very slowly, I'm going to get some, I mean, my experience with LDL cholesterol, this is something I changed my mind on a while back. When I was younger, like circa 2005, getting into grad school, kind of the prevailing thought was, well, it's not so much the LDL, it's the ratio of LDL to HDL that's what matters. And probably about 5 years ago, and I was pretty strong about that opinion. And then 5 years ago, looking at these Mendelian randomization studies, I kind of went, I can't hold this position anymore.
What is your revised position on LDL?
So if you look at the research, HDL is important because it's a marker of metabolic health. If you have high HDL, it suggests that you are metabolically quite healthy. You very rarely will you have high HDL and like high CRP, which is an inflammatory marker, or dysregulated blood glucose. Almost exclusively, people who have high HDL will have good biomarkers of metabolic health. But if you take drugs that raise HDL, it doesn't reduce your risk of cardiovascular disease. In Mendelian randomization studies, which Mendelian randomization basically uses natural randomization. So some people are, in the case of HDL, naturally higher secretors or naturally lower secretors of HDL. And, we talked about how you can't really do a 20-year human randomized control trial. And when you're trying to examine something like heart disease, I mean, that is a lifetime exposure issue. It's very unlikely that you're going to pick out differences between treatments in 2 years or even 5 years. I mean, people typically don't develop heart disease until they're in their 50s, 60s, and 70s. What Mendelian randomization allows is to say, okay, we have these people who naturally secrete more or less, so we can stratify those and look at what is their risk. So if you look at people who are low secretors of HDL versus high secretors of HDL, with holding some of the other key variables consistent like LDL, you don't see an effect on heart disease really.
Of LDL?
Of HDL.
Got it. Okay.
But when you look at LDL and you look at the lifetime exposure to LDL, it is like a linear effect on heart disease. And we know that it's actually not so much LDL, but it's more apolipoprotein B, but that tends to track with LDL just in general. And if you look at the mechanism, I mean, we know that LDL can penetrate the endothelium. So there's the mechanism is present. If we look at the epidemiology, it supports that it's an independent risk factor. And then again, these Mendelian randomization studies where we can kind of look at people's exposure over a lifetime, and then we see that linear kind of dose-dependent effect. To me, that was convincing enough to change my mind on that particular topic. And then if you look at like some of the Framingham data, look at if you like stratify like high HDL versus low HDL, both groups looking at high LDL and low LDL. So if you have high HDL, low LDL, you will still be lower risk factor than somebody who has high HDL and high LDL, right?
So the ratio does matter.
So the ratio does matter. Same thing with inflammation. If you look at people who are low inflammation, low LDL, they'll have a lower risk than people who are low inflammation, high LDL. So again, that was kind of sufficient for me to change my mind. But it was like not just one study came out. It was, okay, then there was another study, and then another study, and then another study. And at a certain point I go, okay, well, now I either have to change my mind or I'm basically just going to be cognitively dissonant and say, nope, I don't believe all that, And so I think that's one of the things to keep in mind. People will say, oh, you're saying this is a bad study. Very rarely will I call something a bad study because data is just data. But the issue becomes how it is presented and how broadly it's applied in the mainstream media or by people on fitness influencers. And what I'll do is try to step in and say, okay, let's consider X, Y, and Z as well. And then it's not a bad study, but let's just be careful about how broadly we imply the interpretation.
Yeah, well, and I think you are in a very unique and important position to be able to place things into their proper context because of this, for lack of a better word, holistic view of how the psychology, placebo effects, also core physiology relate to one another, and so on. In fact, I think that your training as a biochemist and then training as in nutrition with somebody who, Don Layman, who was pushing you to focus on outcomes, I think that's a beautiful capture of the continuum at which one can look at something. Because for those of you who don't know out there, a lot of laboratory studies on mice and humans, for instance, in the realm of biochemistry or in vitro studies, you'll see a change in some molecule can be quite dramatic. And then the assumption is, you just take the drug that will change that molecule in a particular direction, and then you'll get the effect you want at the whole organism level. The person will lose weight. The person will gain muscle. The animal will not have Alzheimer's, et cetera. But it just doesn't work that way because of the redundancy and this interplay.
Well, a great example of that is, so my research was actually in rodents. All my studies on protein metabolism and leucine in particular is what we were studying. Well, we know if you give leucine, it increases muscle protein synthesis. But we also know if you supplement with leucine, people don't get more muscular.
I was about to say, so all you have to do is supplement with leucine?
Right. And so how is that possible? Where, muscle building is not just protein synthesis. It's also the balance between synthesis and degradation. So, and degradation just happens to be very, very difficult to measure. But a great example, and again, one of the cool things about my PhD was actually change the way I ate, which I think is interesting. So before I had been like, I eat 8 meals a day, eat every 2 hours, try to keep
8 meals a day.
Yeah, when I got to grad school.
In order to hit that 30 grams of protein per meal.
Get that amino drip going in was the idea, right? Like just have an IV hooked up with amino acids.
Not really, folks.
Not really, yeah. But that was kind of the concept. But the first study I did, we basically looked at, okay, a lot of people had measured the amplitude of protein synthesis in response to a meal. We wanted to see how long does this last and where does it peak, right? And so my thought was, okay, well, it'll probably track with plasma leucine. You give, for those that are not familiar, leucine is the amino acid that is almost exclusively responsible for increasing muscle protein synthesis when you eat protein. So it's one of the branched chain amino acids. So we wanted to see, okay, how long does this effect last? So we fed these animals whey protein. And again, I thought, okay, well, however long plasma leucine stays up, that will be how long protein synthesis stays up. And so we got the protein synthesis data back, and it was peaked from 45 to 90 minutes, and then was back down to baseline by 180 minutes. And so when I went to do the plasma leucine analysis, my shock was at 3 hours, plasma leucine was still plateaued out. And I said, okay, well, when I look at the initiation factors, that will show me something. So for those not familiar, this is part of the mTOR signaling pathway. So two of the targets of mTOR, when it's stimulated, leucine stimulates mTOR. Two of the targets of mTOR are a protein compound called 4-EBP1, and then another one is called ribosomal protein S6K. So I don't want to get into the specifics about it because it's kind of beyond the scope, but basically when these things are phosphorylated by mTOR, it increases the rate of translation initiation, which translation initiation is basically the process of the ribosome hooking on to the mRNA and then starting protein synthesis. So I was looking at the phosphorylation of 4-EBP1 and RPS6. I was like, okay, well, I'll probably see these things come down at 3 hours. Still plateaued. And so then it was like, what's going on here? So I actually kept rerunning the data and rerunning the data and rerunning the data. And I'll never forget, I went into Layman's office, and this is like, 6 months after we've done this study, because this analysis takes time. He's like, so where are we with this duration study? I said, well, I just got to run the plasma data again because it's not right. And he's like, well, why is it not right? And I said, well, it just doesn't make any sense, And I kind of went through, he's like, well, describe to me your technique. Like, how are you doing this? And I described it. And he said, well, how's your standard error? And I told him what the numbers were. He said, it sounds like it's good data. He said, it sounds like you are trying to get the data to fit your conclusion, and you need to change your conclusion to fit the data. And that statement,
This is why we do PhDs.
this
right?
is why, yeah.
You need an advisor.
This is why I'm so skeptical of everything, because I have had so many of my ideas crushed by my own data, right? So we actually ended up, this kind of effect, this phenomenon is called muscle protein synthetic refractory period. So basically, like once you trigger the system, kind of runs for a defined period of time, and then it takes time to essentially like reset, for lack of a better term. It's also been referred to as the muscle full effect. But so I looked at that and said, why am I eating every 2 hours then? You know, and there was even a study out of Wolf's lab, like back in '99, I think, where they infused essential amino acids for 6 hours. Protein synthesis went up, peaked at 60 minutes, came back down at 120, and never went back up again.
Maybe I'm being naive, but I would have thought that if protein synthesis goes up and then comes back down, that eating more often would be exactly the thing you would want to do if your goal was to get increased protein synthesis, because you'd be pinging the system periodically.
But the problem is the plasma amino acids are still elevated.
So it's essentially like eating the whole way through,
Right.
From the perspective of leucine.
From the cells,
Got
yeah.
it.
So that was one of those things where I said, you know what, I'm actually going to eat less often, because like if I'm eating and 3 hours later, I've still got, capped out plasma amino acids, and we looked at all kinds of stuff. Like we looked at intracellular leucine just to make sure that, that wasn't falling off. It wasn't. We looked at all the plasma essential amino acids because we were thinking, well, maybe protein synthesis is, sucking some of these amino acids out of the plasma and they're dropping, and that's causing it to kind of short circuit the system. That wasn't the case. It just essentially what the evidence suggests, I think we're the only ones to show this so far. So I'm not ready to say that this is a real effect, because I hold out the idea that data artifacts do exist and you can't be totally sure. But we saw an increase in AMP kinase kind of around this mark where protein synthesis started falling off. And we also saw a decrease in intracellular ATP. And protein synthesis is an ATP-dependent process. And so what we think might be happening is you're, consuming protein and you're increasing